Right, welcome back. I hope that the previous hour was fruitful and that you have maybe learned something and the insight is been bettered. Right, we are going to move on to the next example. Right, question 11. Diesel electric trains make use of electric motors as well as generators. Right. Now the question, the table below compares the motor and the generator in terms of the type of energy conversions and the underlying principle on which each operates. Complete the table. Right. Now the motor, and remember, the only type of motor we do is now the direct current motor, just for interest's sake, and generators we can use both AC or DC. The type of energy conversion in electric motor, right? Like we have said in the previous examples, we start off with electrical energy, and then it's transferred to mechanical. So that is very easy, and I think you know it at this stage. And in a generator, it's just the opposite. It's mechanical to electrical. Right. Then the principle on which this motor and generator operates. And again, the principle is the motor effects. Some learners sometimes write down Fleming's rule. That is maybe the more second choice answer. So I'll stick to the motor effect. That is the best way of answering this. And then you all know that the principle for the working of a generator is electromagnetic induction. Electromagnetic induction. Right. The simplified diagram below represents an electric motor. Give a reason why the section label of the coil labeled BC in the above diagram does not experience a magnetic force while the coil is in the position as shown. Right. Firstly, you must we take this as that this switch is closed. So please don't use this as an answer. So we close this switch. The switch is closed. So therefore, why does this section don't experience a magnetic force in this electric motor? And the reason is because the conductor, the part of the conductor, and the charge is parallel to the to the magnetic field, and therefore it experiences no force. 11.3, two graphs are given to you. A graph of the alternating current against time and the potential difference against time. The graph indicates that is alternating current. Now the question, calculate the average power output of this generator. So now they don't give you any values directly, they give the values indirectly by means of a graph. Just move this a little bit upward. Right. Again, you can go back to your data sheet, and now in this instance you will see that they give you Imax and Vmax. They are looking for the average power generated in this question. And now this formula indicates that you need the VRMS and the IRMS. So definitely you will use these two formulas to calculate IRMS and VRMS. So the first step now is to calculate, say for instance, let us start at VRMS, and we derive the values from this graph. they indicate to you that the maximum potential difference induced is maximum potential difference induced is 311 volts. So V max, therefore, derived from the graph equals 311 divided by the square root of 2. And you get your answer. Again, IRMS you can calculate by making use of the value given here for I max. So it is I max divided by square root of 2. So it is 21 divided by square root of 2, and you get your answer. And now you are able to go back to your formula P average equals VRMS times IRMS. Okay, and you just substitute those two values that you have calculated here. So this is the only different way of something different in this question is that they make use of graphs to indicate the different values to you. Right. We're moving on to the next question. Right. Let me just, I have a question. Let me just move back to question. I have a question from let me see, a learner from Totagauta Secondary School, and Sempi asked, why is 3000 volt written as VRMS in the question? Let me just move back to the previous problems. Maybe I've made a mistake there. I'm just going backwards. Just previous question. Okay. Right. Okay. Sempi is correct in this instance. This value here, I've misread that it's given as the maximum voltage. So what must we first do? We must first calculate a VRMS. First calculate VRMS by means of Vmax over square root 2. And so it will be 30,000 volt divided by square root of 2. And then that value you substitute into this formula, and you use that value for VRMS. Thank you, Sempe. And Tikoi, if I pronounce it correctly, that you have observed that. It shows that you are really with me in this discussion. Thank you for that. Right. Moving back to the next question. And here's an example, again, of the typical multiple choice question on electrical motors and generators. You will see, I think, the last, 4 or 5 years, I think 3 out of 5 times, such type of a question was asked in the multiple choice questions. The cross in the diagram below represents a conductor carrying conventional current into the base. In fact, they help you to tell you that because you're supposed to know it yourself. And it's between 2 bar magnets. And you will therefore see that the direction of the magnetic field is from north to south. The question then is, the conductor is placed between that. The question is, in which one of the directions, A, B, C, or D, will the conductor experience a force, all lying in the plane of the page? Now, which rule must you apply? In this instance, the current is given to you, so you started with electrical energy, and then there's a mechanical energy produced, or mechanical energy is a transferred energy. Right, so therefore you must use Fleming's left-hand motor rule, or then the right-hand rule to indicate the direction. If I apply Fleming's right-hand rule, index finger from north to south, the middle finger is directly downwards, away from you into the page, and then my thumb is showing in the direction of C. So your answer to this question will be therefore C. So make sure that if you apply Fleming's left-hand motor rule or the right-hand rule, when you use the palm of the hand to indicate the direction of the force, that you agree with me that you will get the answer as in the direction of C. Right. Question 13. And you will see there's really a few basic type of questions on motors and generators that they are asking you. You always may be giving a sketch and questions asked about the generator or the motor from the sketch, etc. So again, like I've said yesterday, really with electrical motors, with generators, and with the calculations on alternating current, that is questions where you really can make sure that you obtain your marks. If you just will be able to do this type of answer, this type of questions we are looking at. Right, you will then look at the diagram and you will see it's a splitting commutator, and it's very important that the word split ring must be here. If I can maybe in a sense correct this split ring, two words, split ring commutator, and now it's indicated that the coil rotates. It seems that it rotates clockwise, looking at this arrow. Let us look at the first question. Name the component which ensures continuous rotation of the coil of this electric motor. So they describe the function of the split ring commutator. And you must please split ring commutator as then the answer to this question, because this ensures the rotation. This is a function of the split ring commutator. Right, 13.2. Name the part of the motor which becomes an electromagnet when the current flows in the motor. An electromagnet. Why does this coil rotate? That is a question. You have a permanent magnet, so why does this copper wire, copper doesn't experience influence of a magnetic field on its own, so why does this copper wire experience a force? That is because when the current starts to flow in this conductor, in this coil, then this coil becomes an electromagnet, and then two magnetic fields is attracting and repulsing each other, causing the motion. So you must then have your answer ready as the coil is the part of this motor which causes to be an electromagnet. Right, question 13.3. When the electric motor is connected to a 12-volt DC supply, direct current supply, it draws a current of 1,2 amperes. The motor is now used to lift an object of mass 1,6 kg through a vertical height of 0,8 meters at constant speed in 3 seconds. Now you will see they are bringing in, the idea of work done, of gravitational potential energy, sorry for that. They combine this with your equation on alternating current. So let's make sure what is the data given to us. Right. You have the potential difference of an electric motor is direct current, and very important, a direct current. It draws current of 1,2 amperes, right? So immediately you will see that you are able to calculate the power used by the electric motor by means of VI. But let's go on. The motor is now used to lift an object of the mass 1,6 kilogram. So if you have a mass of 1,6 kilogram through a vertical height of 0,8, you have a height, or you can say delta y as 0,8 meters, and the time given to you is 3 seconds. Right. What can you do with this data given to you? You can calculate the power needed to do this job, to lift this water, or what is it, the mass, the mass of 1,6 kilogram through a height of 0,8 meters. So what is the work done by this by the motor on this object? The formula for work done, is the force times the displacement or the distance moved times cos theta. So therefore, the force in this instance is gravitational force, and we know gravitational force is m times g. The distance traveled by this object, delta y, is 0,8 meters. Okay, let us just write it as delta y, and then cos theta. And cos theta in this instance, the direction of delta y is upwards, but the force, the gravitational force, is downwards. So the angle between the motion and the force is 180 degrees. So your complete formula, if you substitute everything, will be 1,6 times 9,8 for gravitational acceleration times 0,8 meters times cos 180, and times cos 180 will be minus 1. Right, and then you will get an answer. You maybe can also just state that the gravitational potential energy gained was, just write it down as EP equals mgh, because you're only looking at the value of the magnitude of the energy gained, gravitational potential energy gained, and then you can also write it as 1,6 times 9,8 times 0,8, and you see we'll get the same answer in the sense of the magnitude. This is only indicating that the direction of the force and the displacement is opposite. Right, and you will get your value here. Unfortunately, I don't have my calculator here to get an answer, but I'm sure you will get it there where you are sitting. Right, now you have the work done, or the electric potential energy gained. But you must now calculate the power, because the question is all the electrical energy converted to gain potential energy in this instance? Right. The power dissipated, or the power used by the motor, is 12 volt times 1,2 amperes. Right, and that will roughly give you a value. It's 12, and it's 1/5 of that is, I think, 2,12 and maybe 2,4. So let's say, for instance, if it is wrong, we can only use this value. It's 14,4. It's 14,4 watt. And now the power, the real work, the real power that this electric motor has done is the following. It is the power also equals mechanical energy, the energy transferred or the work done divided by the time the work is done, in which work is done. So then you will take this value, unfortunately I have no answer, this value, and divide it by, you will see that it's lifted within 3 seconds. And you 3 seconds in this instance, and then you compare your two answers. You compare your two answers. And if this answer is smaller than the actual that the motor was supposed to generate, the power that the motor was supposed to generate, but the real power, work per second done on this object is less, then you know that all the work done on the electrical motor, all the electrical energy in that sense isn't converted to gravitational potential energy. There's certainly another way of doing that, and that is to calculate directly the work done, and you will know that there's an alternative, there's a formula for energy, so you can use this formula. You have the time as 3 seconds, so you can calculate the energy, electrical energy used, and then also in this sense here, if you maybe have calculated the power that was really transferred on the object, then you can again make use of the calculation of, let me just see, power differentiated, okay, and then you calculate the work done. Let me just see if this is possible. If I'm not right, the work done, you can calculate. Okay, that's not necessary. Then you simply compare this value calculated here in one of these two options, and you can just compare it with that value there. And if this is less than this value, then you can state that not all the electrical energy is converted to gravitational potential energy. But I think maybe the easiest is to maybe calculate the power dissipated by the motor and the real power transferred to the object. I'm really not sure if this formula is indicated on the data sheet. If this is indicated on the data sheet, it is maybe also a real useful method of comparing directly the two energies to each other. So then you will have this calculation, all this calculation for the work done here, and you compare it with the electrical, the power dissipated by the electrical or used by electrical motor. Right, this is the types of questions we normally get in this in the AC alternating current generator and motor topics. So I hope that this maybe will give you some insight and help you to answer your questions properly next Friday when you write the physics paper. If there's no questions received from you, I'll my best wishes with you in your studies, and maybe I'll again see you later this next week maybe on work and energy and power, mechanical power. So all of the best for your revision and the next subject you write, and maybe see you then maybe next week.